We move through space as if three directions are all that exist, yet physics keeps suggesting otherwise. Again and again, when scientists push their equations far enough, extra dimensions appear, not as speculation, but as necessity. Hidden, compact, and beyond direct perception, they may be part of the same space we already inhabit. So, the question is simple. If one more spatial dimension were suddenly accessible, what would we actually see? Physics often advances through moments when familiar explanations no longer hold, when equations that once felt complete suddenly reveal gaps. The story of extra dimensions begins exactly at such a moment when the known laws of nature began to resist being placed under one roof. Early in the 20th century, gravity had just been reimagined. No longer a force acting at a distance, it became a geometric feature of space-time itself, a curvature caused by mass and energy. Einstein's general relativity offered a picture more elegant than anything before it. Planets orbited stars not because they were pulled, but because they followed the natural paths carved into the fabric of space-time. This insight shifted physics from a world of invisible forces into a universe shaped by geometry. Yet there remained another force, one that permeated daily life, one that controlled light, chemistry, and behavior of matter: electromagnetism. Maxwell's equations described its behavior perfectly, but nothing linked these equations to Einstein's curved space-time. Gravity felt geometric, electromagnetism felt algebraic. No bridge seemed to connect them. This is where the first whisper of an extra dimension appeared, quiet, almost accidental, but profound enough to become the seed of nearly every higher dimensional theory that came afterward. Theodore Kaluza, a mathematician with a knack for seeing structure where others saw chaos, asked a question that bordered on audacious simplicity. What if electromagnetism could also be geometry? If gravity emerged from curvature in 4 dimensions, perhaps a second fundamental force might emerge from curvature in a slightly larger geometric space. Instead of changing the equations, Kaluza changed the stage. He took Einstein's framework and extended it from 4 dimensions, 3 of space and 1 of time, into a 5-dimensional space-time. This additional dimension was not introduced to be dramatic. It was introduced because the mathematics seemed to have room for it. When Kaluza expanded the metric tensor from a 4C4 object to a 5-1, new components naturally appeared. Some of these components looked unfamiliar, but others looked uncannily like the electromagnetic vector potential, the very structure from which Maxwell's equations arise. When he inserted this 5-dimensional metric into Einstein's field equations and worked through the calculations, an astonishing result emerged. The equations split cleanly into 2 sets. One set reproduced Einstein's original gravitational equations. The other reproduced Maxwell's equations for electromagnetism. 2 fundamental forces described by one geometry, emerging from one extended space-time. It was the first glimpse of unification, a moment when physics briefly felt as though its deep structure might be simpler than expected, as though the forces shaping the universe were shadows of a higher spatial architecture. But Kaluza's idea, inspiring as it was, left a problem unresolved. If a 5th dimension existed, why was it never observed? Why did objects move freely in 3 dimensions, but never slip into a 4th spatial direction? Oscar Klein, working in the early days of quantum theory, offered an explanation that blended geometry with the strange, newly discovered world of the microscopic. Klein proposed that the 5th dimension did exist, but it was not extended and spacious like the familiar ones. Instead, it was curled tightly upon itself, forming a loop so small, perhaps around 10 30s and 10 skostits to 30, 10 30 meters in circumference, that no organism, object, or instrument could detect motion through it. Just as the surface of a cable looks one-dimensional from far away but reveals a tiny circular dimension when examined closely, space-time itself might host hidden directions too small to enter or perceive. This idea of compactification, of a dimension rolled into a microscopic circle, became one of the most influential concepts in theoretical physics. It preserved Kaluza's unification while explaining invisibility. To move in 3 dimensions required almost no energy. To move in the compactified direction required enormous energy, far beyond what nature appeared to provide. In practice, the 5th dimension was present but inaccessible, a hidden thread woven into the fabric of the universe. For a time, The Kaluza-Klein model looked like a glimpse of the universe's deeper order, but cracks began to appear. When physicists applied the model to electrons, the predicted properties failed to align with experimental data. Charges came out wrong, mass came out wrong. The theory reproduced electromagnetism beautifully, but stumbled when asked to describe matter itself. And as physics entered the quantum era, two incompatible frameworks emerged: relativity, governing the cosmic scale, and quantum mechanics, governing the microscopic. Kaluza-Klein unification could not reconcile them. By mid-century, the theory faded from mainstream research. Yet it never truly disappeared. Its central idea, that forces might emerge from geometry in higher dimensions, proved too elegant to abandon. Even in failure, it had shown something extraordinary. Adding dimensions was not an act of fantasy, but a mathematically natural way to deepen understanding. When later generations of physicists confronted new problems, they rediscovered the blueprint that Kaluza and Klein had drawn. The resurgence came with string theory, a framework that treated particles not as points, but as vibrating one-dimensional strings. These strings behaved consistently only in a universe with more than the familiar 4 dimensions, not just 5, 10. Later, M-theory extended the structure again, suggesting an 11th dimension in which higher dimensional membranes, or brains, could exist and interact. Suddenly, the old Kaluza-Klein idea was not an odd historical footnote, but a precursor. Compactified dimensions re-entered theoretical physics, with new meaning. String vibrations depended on their geometry, and entire particle families emerged from the shape of curled-up spaces called Calabi-Yau manifolds. In this light, the first extra dimension was not the wrong answer. It was the first step towards seeing the universe as a multi-layered object, whose true form might be permanently hidden from direct perception. What mattered was not the specific details Kaluza proposed, but the deeper principle he uncovered. The laws of nature may arise because space-time itself possesses more structure than 3 spatial directions allow. This principle carries profound implications. If dimensions can be compactified, they might exist at every point in space, folded so tightly that even the smallest known particles cannot explore them. If physical forces emerge from geometry, then understanding the universe might require mapping the unseen dimensions that shape its structure. And if the familiar world is only a projection, a slice, through a richer environment, then everything in existence may be less complete than it appears. The subtlety of Klein's insight often goes unnoticed. A curled dimension does not vanish. It hides in plain sight, influencing the behavior of particles and fields without ever revealing itself directly. Such a dimension could be woven through every atom, every photon, every point in space-time. The universe might be saturated with extra directions, yet no biological organism or mechanical instrument has ever been able to stretch far enough or small enough to enter them. This leads naturally to a quiet but haunting question, one that sits at the center of this part of the journey. What if an extra dimension sits at every point in space, yet remains too curled to see? In that possibility lies the foundation for modern theories of unification, for the effort to reconcile quantum physics with relativity, and for the later, more radical idea that an entire universe might float as a membrane within a higher dimensional bulk. Kaluza-Klein theory did not complete the story, but it changed the map of reality. It showed that adding dimensions could reveal structure where none was previously visible. It hinted that physics might progress not by expanding equations, but by enlarging the stage on which they play out. Human perception offers only a narrow window shaped by evolution, and the dimensions that matter most to the universe may be the ones that remain hidden. If the observable world is merely a projection of a higher dimensional object, every attempt to understand higher dimensions begins with a challenge. The human mind has never experienced them directly. The limits of perception create a quiet barrier, shaping what seems possible. One of the clearest ways to loosen those limits is to imagine a world simpler than our own, so simple that its inhabitants cannot conceive of us at all. Edwin Abbott called it Flatland, a realm of perfect two-dimensional existence. Though fictional, the analogy reveals something fundamental about how dimensions hide themselves, and why even a universe filled with higher spatial directions could remain unseen. In Flatland, every creature lives fully within a plane. A square moves by sliding left or right, forward or backward, but never up or down. That missing direction is not forbidden. It simply does not exist within the creature's sensory or physical repertoire. To them, the plane is complete. Life unfolds along a map of edges and polygons, and nothing suggests the presence of a wider world. Yet, a being from 3 dimensions could descend effortlessly into this universe. It could hover above the plane, watching the shapes glide beneath like shadows. It could touch them, even pass through their closed boundaries, and their inhabitants would have no vocabulary to describe the intrusion. When a sphere enters Flatland, the experience from each perspective becomes profoundly different. The sphere encounters the plane as a volume interacting with a sheet of geometry. But, to a Flatlander, only a thin slice of the sphere is visible at any moment. As the sphere dips lower, a point appears, expands to a growing circle, then contracts again before disappearing. The creature in Flatland never sees the sphere as a whole object, only the evolving cross-sections. The completeness of the 3-dimensional form remains inaccessible. This single image, familiar from countless physics discussions, becomes a quiet mirror. It reflects back the possibility that 3-dimensional beings may experience higher dimensions in equally fragmented ways. If a 4-dimensional entity intersected the familiar world, the event might appear not as a coherent body, but as shifting slices, objects emerging, changing shape, fading away without apparent cause. What appears impossible may simply be a misunderstanding of projection. Neil deGrasse Tyson once described the consequences of such geometry with a kind of calm astonishment. A 3-dimensional surgeon, looking down onto Flatland, could see straight into the bodies of its inhabitants. Internal organs would be visible without incision, because their boundaries exist only within the plane. By lifting a Flatlander into the 3rd dimension, the surgeon could flip the shape, reverse orientation, or remove an object from within without ever breaking the creature's perimeter. What seems like magic to the 2-dimensional observer is no more than a higher dimensional motion. For a 4-dimensional being, 3-dimensional anatomy would be equally transparent. Skin would no longer function as a boundary. Bones and organs would sit exposed to higher dimensional sight, as openly as lines drawn on paper. Even a sealed room would offer no confinement. A 4th spatial direction would allow entry or exit without disturbing walls, ceilings, or floors. In this sense, enclosure is not an absolute concept, but a product of dimensional availability. Such thought, experiments are not attempts to dramatize the unknown. They illustrate something quieter. Just as Flatlanders cannot imagine up, 3-dimensional beings cannot visualize a spatial direction orthogonal to all the ones they know. This does not imply the absence of such a direction. It only indicates a cognitive limit. Geometry does not depend on intuition to exist. The difficulty arises from the nature of perception. Eyes capture light, projected onto a 2-dimensional surface. The brain reconstructs depth through layered processing. Reality becomes a 3-dimensional model built from 2-dimensional inputs. If another spatial dimension existed, the senses would not be equipped to detect it directly. Even if an object extended into that dimension, only its 3-dimensional trace would be visible, just as the Flatlander sees only a circular slice of the intersecting sphere. This idea that higher dimensions may remain hidden because of perceptual reconstruction forms a bridge between the simplicity of Flatland and the complexity of modern physics. The question shifts from, do higher dimensions exist, to what shape would evidence take if they did? A 4-dimensional object passing through space would not resemble a singular form. It would resemble a sequence of temporary shapes appearing and dissolving. A solid might become hollow, then solid again. Boundaries might open and close without force. The event would look less like the movement of an object and more like the transformation of reality itself. Mathematically, this behavior is perfectly ordinary. A slice through a tesseract, a 4-dimensional analog of a cube, reveals a cascade of polyhedral forms as the hypercube intersects 3-dimensional space. Each slice is complete within the dimension it inhabits, but incomplete relative to the higher form. The mind struggles not because the mathematics is complicated, but because the underlying geometry refuses to conform to visual habits built within a lower dimensional world. This perspective clarifies something profound. 3-dimensional beings are not uniquely limited. All dimensional creatures are. In Flatland, no amount of introspection reveals the vertical axis. In 3-dimensional space, No amount of visualization yields a clear intuition for a fourth spatial axis. Just as a drawing on paper cannot step into volume, a body embedded in volume cannot naturally step into hyperspace. Each realm has boundaries defined not by laws of physics, but by the structure of its dimensional embedding. These boundaries shape expectations. Surfaces seem solid. Containers seem closed. The inside of a body seems inaccessible without incision. In a higher dimension, none of these conclusions would persist. The distinction between interior and exterior is a feature of three dimensions, not a universal truth. A sphere intersecting the plane creates a circle. A tesseract intersecting space creates a sequence of shapes. In each case, the lower dimension receives only a projection, not the full object. This insight sets the stage for the central question. If higher spatial dimensions exist, how often might their effects appear as inexplicable events? Physics does not propose that beings slip in and out of hyperspace, but it acknowledges that many features of fields and forces can be understood as projections of higher structures. In Kaluza-Klein theory, electromagnetism becomes a geometric shadow cast by a compactified dimension. In string theory, particle types arise from the vibrational patterns of strings resonating in curled spaces invisible to ordinary perception. The logic echoes Flatland. Unseen dimensions create visible consequences. The analogy extends further. A Flatlander might attempt to describe the sudden appearance of a sphere's slice as a creation event, not realizing the slice is only a partial view. A fragment of a higher dimensional body might appear to change shape without reason, not because the object is changing, but because the intersection between dimensions is shifting. In the same way, certain puzzles in physics, like why gravity weakens more quickly than expected, or why particle families come in structured sets, may be signs of higher dimensional geometry. These are not definitive conclusions, but they are reminders that projection can mislead. The entire exercise carries a deeper implication about perception. The boundaries of the familiar world may not be absolute. They may be artifacts of limited perspective, just as Flatland's inhabitants believe their plane is the only possible stage for existence. Modern theories do not claim to see higher dimensions directly. They claim that mathematics and observation align more naturally when extra dimensions are included. The structures of particles, forces, and space-time behave as if geometry extends beyond three dimensions, even if those dimensions remain beyond sight. Flatland, despite its simplicity, becomes a powerful guide. It demonstrates that inability to perceive does not equate to non-existence. A missing dimension is not a void. It is an unperceived richness. The analogy invites a quiet reconsideration of what complete means in physical reality. A two-dimensional world feels complete to its inhabitants. So, does a three-dimensional one. A higher dimensional universe could feel equally complete to beings capable of sensing it. Among all the questions raised by this analogy, one remains particularly soft yet persistent. A natural wonder growing from the logic rather than from speculation. If a higher dimensional entity passed through the familiar world, would only fragments of its form be visible? This question does not seek evidence. It seeks understanding. It highlights the central theme of dimensional thinking. What is seen is not always what exists. Projections define perception, and the mind forms its understanding from the limited cross-sections provided by the senses. Just as Flatland cannot grasp a sphere, a three-dimensional perspective cannot fully grasp a tesseract, yet both remain real within their respective geometries. Time often feels like an invisible current, carrying every event forward with a quiet certainty. Days unfold in a sequence that can never be rewound, and a life traces a single unbranching arc from birth to its final moment. This experience creates an impression of inevitability, as though time is a river that permits only one direction of travel. Yet physics treats time not as a flow, but as a coordinate, one that stands alongside the familiar spatial axes. In this framework, every moment is a point in a larger structure, and the motion through time is not guided by an outside force, but by the geometry of space-time itself. Einstein's formulation of relativity transformed time into a dimension woven inseparably with space. A location becomes meaningful only when paired with a moment. A meeting, a collision, or even a single heartbeat is not merely where something occurs, but when. The path of an object through the universe forms a continuous line, its world line, representing every position it occupies as time advances. This world line encodes the entire history of that object, even though the object itself experiences only one instant at a time. To the mathematics, all points on the world line exist simultaneously. To the object moving along it, only the current point holds awareness. The tension between these two viewpoints opens a small window into what a higher dimensional perspective might entail. If time is simply another dimension, then a being capable of navigating it freely would not encounter events in sequence, but as an extended structure. A lifetime would not unfold. It would stand still, much like a panoramic image containing all its details at once. From within, the image feels like a journey. From above, it is a single geometric form. This distinction becomes clearer when considering relativistic thought experiments. The twin paradox presents a scenario where two identical individuals follow different world lines due to differences in motion. One remains on Earth, while the other embarks on a high-speed journey through space. Upon returning, the traveling twin has aged less than the one who stayed behind. The discrepancy is not a trick of perception, but a difference in the lengths of their respective world lines through space-time. Though each twin experiences a steady, personal progression of time, the geometry of their paths alters the total duration they accumulate. This paradox highlights a subtle idea. The flow of time depends on the path taken, not on an absolute ticking clock. If a higher dimensional observer could view both world lines from an external vantage, the difference would not appear mysterious. The paths would be laid out fully, and the relationship between them would be as clear as two curves drawn on a page. The observer would not ask why one twin aged differently, but would simply see that the shapes of their trajectories were not the same. In the context of dimensional thinking, this perspective resembles the conceptual difference between what might be called alpha and beta levels of perception. An alpha-level viewpoint corresponds to ordinary experience, awareness bound to a single sequence of moments, unable to leave its own world line. A beta-level viewpoint resembles a step outward, one that sees the sequence but is not contained within it. From this higher vantage, time is not a direction of travel, but a dimension of structure. Events no longer chase one another. Instead, they coexist, arranged in patterns that can be inspected without participating in the flow. The distinction becomes more vivid with an analogy from recorded media. For the alpha perspective, a film unspools frame by frame. There is a beginning, a middle, and an end, each encountered only in the order the reel dictates. But the beta perspective resembles the vantage of one who holds the entire reel in hand, able to examine any frame at will. The story does not change, but the relationship to the story does. The sense of being carried along vanishes, replaced by an awareness of the whole. Physics does not suggest that consciousness can detach from its world line, yet the analogy helps illuminate what is meant by seeing time from above. The geometry of space-time already contains all events. Only the experience of those events is sequential. A higher dimensional being, capable of perceiving the entire world line of a particle, a star, or a human life, would not witness surprises. The structure would be fixed, even though the contents of the structure include actions, decisions, and unfolding complexity. Such a perspective would not intervene in the world. It would simply observe its temporal architecture. The idea was extended in a striking way by the philosopher and engineer J.W. Dunn, who proposed that the human sense of passing time might itself be only one layer in a multi-tiered structure. In Dunn's formulation, awareness observes the movement of the present moment along a world line. But for that observation to occur, Dunn argued, there must be a second dimension of time, a meta-time, in which the movement through ordinary time takes place. And if awareness tracks the progression through meta-time, another layer might be required to observe that movement as well. Dunn's hierarchy grows quickly, though not because he intended to describe an infinite cosmos. Rather, he used the idea to highlight the difficulty of explaining temporal experience within a single-dimensional time. Modern physics does not adopt Dunn's infinite regress, but the discussion introduces an intriguing possibility. Perspectives about time are relative to the dimensional framework within which they operate. Just as 3 spatial dimensions feel sufficient from within, one temporal dimension feels complete only because perception is shaped by it. A higher dimensional being might consider an entire lifetime as a static entity. as familiar and ordinary as a mountain range viewed from above. Rising into such a dimensional vantage does not alter the events themselves. It alters the relation to them. This shift in perspective clarifies something about dimensional constraints. Limited movement through time is not a fundamental rule of the universe, but a property of embodiment within space-time. A being confined to a world line cannot reverse its direction or pause its progression. It experiences time as motion because it inhabits the dimension internally. But a being embedded in a higher dimensional framework could plausibly interact with temporal structure differently, seeing the totality rather than the sequence. Even if such beings remain hypothetical, their imagined perspective helps illuminate why time behaves so differently from space. Despite both being dimensions of the same geometric fabric, the implications of such a viewpoint reach beyond abstract speculation. In relativistic thought experiments, events separated in time for one observer may be simultaneous for another. The notion of now dissolves under transformation. A higher dimensional observer would not need to reconcile these differences. They would see them as aspects of a unified structure. The line between past and future becomes a matter of perspective, not an absolute boundary. This does not suggest that ordinary beings could step out of their world lines or alter their sequences of events. Physics remains consistent. Movement through time is constrained by the structure of space-time, and causality retains its coherence. Rather, the exploration points to a deeper understanding. The apparent flow of time arises from a limited vantage within a four-dimensional continuum. The idea of layers of perception, alpha moving through time, beta viewing the timeline as a whole, gamma perceiving relationships among multiple possible timelines, does not propose supernatural entities. Instead, it offers a conceptual ladder for understanding how dimensionality changes the nature of observation. A gamma-level perspective, described in theoretical contexts, suggests awareness of an entire landscape of temporal variations, not just a single fixed world line. Again, physics does not claim such beings exist. It only demonstrates that mathematical structures allow such viewpoints without contradiction. These conceptual models create a foundation for later chapters, where the notion of stepping into higher spatial dimensions gains meaning. If time itself behaves differently when viewed from above, then space may also change character when extended beyond the familiar axes. The boundaries that define rooms, bodies, and trajectories in 3 dimensions might appear malleable from a higher dimensional frame. Objects separated in space might be connected by paths invisible from within. The structure of experience would not dissolve but transform, revealing relationships obscured by dimensional limitations. The pursuit of unification has long guided theoretical physics, a steady effort to understand whether the diverse behaviors of matter can emerge from a single underlying principle. Early attempts linked gravity to a hidden dimension, but as quantum theory matured, another challenge appeared. The familiar world, composed of particles with distinct masses, charges, and behaviors, resisted being woven into a tidy geometric story. The deeper physicists probed, the more fragmented the picture became. Unification required a new framework, one that looked beyond point-like particles entirely. That framework began to form in the late 20th century, when a simple yet transformative idea emerged. Perhaps the smallest constituents of the universe are not particles, but tiny vibrating strings. A string has length but no thickness, and its vibrational patterns give rise to the properties that once seemed intrinsic to particles. A photon becomes one mode of vibration, an electron another, a quark still another. Everything familiar, the atoms in a star, the radiation from a distant galaxy, becomes different notes played by the same fundamental object. This conceptual shift was profound. If particles are points, their interactions often produce infinities that obstruct meaningful calculation. But if particles are strings, extended objects with spatial structure, those mathematical problems evaporate. Forces emerge naturally from the way strings split and merge, and the universe becomes a vast orchestra of resonant structures. Yet, the elegance of string theory arrives with a surprising and unavoidable requirement. It only works in a space-time with more dimensions than the 4 that define ordinary experience. In the simplest versions, consistent vibration requires 26 dimensions. Supersymmetric versions, which align more closely with observed physics, require 10. Later developments that unify these variants, collectively called M-theory, reveal an 11th dimension as well. The reason is not aesthetic, but mathematical. In fewer dimensions, the equations produce impossible features, negative probabilities, unstable configurations, or modes that contradict observed physics. When the dimensionality is increased, these inconsistencies vanish and the theory becomes coherent. Extra dimensions are not optional decoration. They are the scaffolding that allows the structure to stand. This need for additional dimensions echoes the spirit of earlier theories but expands it dramatically. The fifth dimension of Kaluza-Klein extended space-time slightly. String theory expands it profoundly. To understand how the additional dimensions remain hidden, one returns again to the idea of compactification, but now with far richer geometry. Instead of a single curled loop, string theory requires 6 compact spatial dimensions, intricately folded into shapes known as Calabi-Yau, manifolds. These manifolds are not simple circles, but elaborate structures with many folds, holes, and curvatures. Their geometry determines the vibrational possibilities of strings, which in turn determine the types of particles that appear in the lower dimensional world. In this sense, the characteristics of matter arise not from arbitrary parameters, but from spatial architecture. The mass of a particle, the strength of its interactions, and even the number of particle families may be shadows of the geometry in those hidden dimensions. A change in the shape of a Calabi-Yau manifold would rewrite the particle spectrum of the universe. The familiar world becomes a low-dimensional projection of a deeper, higher-dimensional structure. Yet string theory does not stop at compactified dimensions. It introduces higher-dimensional objects called branes, surfaces of various dimensionalities on which strings can attach and vibrate. A one-dimensional brane is a string. A two-dimensional brane resembles a membrane. Higher-dimensional branes extend this idea into realms that cannot be visualized directly. In M-theory, the universe itself may reside on a 3-dimensional brane embedded within an 11-dimensional bulk. All known particles, except possibly the graviton, are confined to this brane, unable to travel into the higher dimensional space. This confinement provides a natural explanation for why 3 spatial dimensions seem sufficient. The forces in matter that shape ordinary experience do not explore the higher dimensional environment around them. Gravity, however, behaves differently. Unlike other fields, gravity emerges from the geometry of space-time itself, and its fundamental particle, the graviton, can propagate through the higher dimensional bulk. This idea opens the door to understanding why gravity appears so weak compared to the other fundamental forces. If gravitational influence spreads not only across the brane but into extra dimensions, its apparent strength in the 3-dimensional world becomes diluted. The puzzle of gravity's weakness transforms into a clue pointing toward an unseen dimensional landscape. Branes also introduce a new way to think about cosmic origins. In certain models, the Big Bang is not the birth of space-time from a singular point, but the aftermath of a collision between branes drifting through the higher dimensional bulk. When 2 massive branes approach and interact, energy can concentrate and ignite a period of rapid expansion, resembling the early moments of the universe. Instead of a single isolated beginning, the cosmos becomes one event within a larger dimensional environment. Though speculative, the scenario highlights an important theme. Higher dimensions provide mechanisms that cannot exist in ordinary space-time, reshaping questions about origins, structure, and evolution. These ideas may seem distant from observation, yet they arise from a consistent mathematical foundation. The necessity of extra dimensions is not asserted, it is discovered. Attempts to restrict string theory to fewer dimensions collapse under their own contradictions. Fields refuse to organize. Vibrational modes produce impossibilities. Geometry becomes unstable. The stability of the theory arrives only when the dimensionality is elevated beyond the familiar 4. In this sense, the universe itself seems to demand additional structure, as though its deep logic extends further than perception suggests. The interplay between branes, strings, and extra dimensions forms a multi-layered picture. A particle's identity emerges from the way a string vibrates. That vibration depends on the geometry of the compactified dimensions. Those dimensions are shaped by the presence of branes. The branes drift within an 11-dimensional bulk that may host other branes, each carrying its own 3-dimensional universe. forces, matter, and space-time become participants in a geometric ecosystem connected not by arbitrary parameters, but by the fundamental shape of higher dimensional space. This structure has implications for how the familiar universe is understood. The existence of multiple branes suggests that parallel universes may be a natural feature of higher dimensional cosmology. These parallel worlds would not be separated by distance in the familiar sense, but by position in the extra dimensions. A shift across the bulk could move from one brane to another without traversing any space within the brane itself. Yet the distance along the extra dimension might be immeasurably large or exceedingly small, depending on the geometry. The idea is not invoked to support speculation, but to illustrate how the mathematics of higher dimensional models naturally introduces possibilities that exceed the limitations of ordinary perspective. Another striking feature of these models is that they unify structures that once seemed unrelated. In lower dimensions, particles appear as distinct entities with different roles. In higher dimensions, they emerge from a single kind of object, strings whose vibrations vary. Forces appear as separate phenomena in three-dimensional space. In higher dimensional geometry, they emerge from the same fundamental structure. Even space-time, which seems so fundamental, becomes an emergent feature of brane dynamics. At this level, the universe resembles not a machine composed of parts, but a coherent symphony whose themes and variations arise from a simple core principle. One of the subtler insights of string theory lies in how it reframes the concept of dimensionality itself. Dimensions are not fixed, rigid structures. They may expand or contract, curl, or unfold, depending on energy, geometry, and the dynamics of branes. In the early universe, extra dimensions may have been as large as the familiar ones. Over time, some expanded while others compactified, shaping the universe into its present form. In this sense, dimensionality becomes dynamic. The structure of reality is not imposed from outside, but emerges from the evolution of the system. Amid all this complexity, a quiet clarity emerges. Higher dimensions are not proposed to make the universe more exotic. They are proposed because the mathematics and the physics refuse to work without them. They are tools for resolving contradictions, for stitching together disparate observations into a coherent whole. Each new dimension is introduced reluctantly, accepted only when the alternative is inconsistency. Higher dimensions enter theoretical physics not as inventions but as necessities, arising whenever equations demand more room to function without contradiction. Yet, despite their mathematical coherence, none of these extra directions appear in daily experience. The world presents itself with three spatial dimensions so consistently that the idea of additional ones seems abstract, distant, almost detached from physical reality. Understanding why they remain hidden requires a shift from asking what dimensions are to asking how physical systems access them. Dimensionality, in a practical sense, is not merely the number of directions available, but the number of directions that matter for motion, energy, and perception. When a surface is examined from afar, it may appear flat even if it contains hills and valleys. Only a close inspection reveals the intricacies. Similarly, a structure might have many spatial dimensions, yet only a subset plays a role at scales accessible to organisms or instruments. Geometry becomes a function of scale, not an absolute property experienced uniformly across size ranges. This notion becomes clear through the concept of compactification, a process in which extra dimensions are present but folded into shapes too small to influence everyday motion. In early attempts such as those by Klein, a single additional dimension was envisioned as a minuscule loop at every point in space. Though the universe contained this hidden circular direction, no ordinary object possessed enough energy to move through it. As a result, all familiar motion occurred within the three macroscopic dimensions, giving the illusion that the curled direction did not exist. Modern theories expand compactification far beyond a single loop. Instead of simple circles, the extra dimensions become six-dimensional spaces with intricate topology. These spaces, known as Calabi-Yau manifolds, may contain countless folds and cavities, shaping the vibrational patterns of strings. Yet, despite their complexity, they remain small, so small that particles moving through familiar space cannot detect their presence. A particle might rotate or oscillate within these curled dimensions. but the resulting effects manifest only in properties such as mass or charge, not in macroscopic movement. Size alone is not the reason these dimensions remain invisible. Human sensory systems evolved to interpret only the features necessary for survival. The eyes detect light within a narrow frequency range. The ears capture a limited band of vibrations. Touch senses pressure, but not the quantum behavior unfolding inside atoms. The neural architecture that interprets these signals constructs a three-dimensional model because 3 dimensions suffice to locate objects, avoid predators, and navigate terrain. Biological evolution had no incentive to develop receptors capable of detecting compactified geometric structures, many orders of magnitude smaller than atomic nuclei. Even scientific instruments extend perception only marginally. Particle accelerators probe the structure of matter by imparting energy to particles, allowing them to explore increasingly smaller scales. But even the most powerful machines cannot reach a regime where compactified dimensions reveal themselves directly. To observe such scales would require energies unattainable with current technology, energies approaching those present only in the earliest moments of cosmic history. Some effects of extra dimensions may still be indirectly accessible. In theories where gravity can propagate through the higher dimensional bulk, gravitational interactions at small scales could deviate slightly from predictions based on three-dimensional physics. Experiments have searched for such deviations by measuring gravitational force at microscopic distances. So far, no conclusive signal has been detected, but the absence of detection remains consistent with dimensions compactified below the experimental threshold. The way fields propagate through spacetime also shapes their relationship to extra dimensions. Electromagnetic, weak and strong forces appear confined to three-dimensional brains. Their force carriers, photons, W and Z bosons, gluons, cannot leave the brain, unable to explore the extra dimensions even if those dimensions exist. Gravity alone differs. Its geometric nature allows it to spread into the bulk. This distinction helps explain both the weakness of gravity and the difficulty of detecting signatures of higher dimensional geometry. If most gravitational influence extends into the bulk, only a diluted remnant reaches the three-dimensional space where observers reside. Compactification and confinement together form a layered picture. Additional dimensions may be woven through every point in space, carrying their own curvatures and dynamics. Yet, three-dimensional life remains tethered to a lower dimensional surface. The familiar properties of matter and force arise not because higher dimensions are absent, but because access to them is limited by energy scale, biological constraints, and the fundamental structure of fields. A more subtle question arises. Even if organisms cannot move through higher dimensions, could higher dimensional effects cast shadows into the three-dimensional world? In some models, the shape of compact dimensions influences the stability of particles. Subtle shifts in the geometry could alter the vibrational patterns of strings, changing particle masses or interaction strengths. Such changes would not reveal the dimensions directly, but would hint at their influence. Detecting such variations, however, would require precision far beyond current capabilities. The invisibility of higher dimensions is further reinforced by the nature of perception. Brains construct models of the world based on patterns and sensory data. These models are not literal representations of external reality, but adaptive frameworks tuned for efficiency. A brain does not represent quantum fields explicitly. It represents objects. It does not depict space-time curvature. It depicts physical distance. In this sense, dimensionality becomes a cognitive construct shaped by the available information. If the information never includes signals from compactified directions, the brain produces a model with only 3 spatial axes. Despite these limitations, theoretical physics offers ways to infer the presence of hidden dimensions through mathematical consistency. When compactification is introduced into equations describing particle interactions, a certain quantities stabilize. Without extra dimensions, theories break down, producing divergences or incompatible predictions. When additional dimensions are added, the structures align, symmetries appear, relationships between particles become coherent. In this way, mathematics becomes a window into realms that direct perception cannot reach. Another path toward understanding invisibility lies in the early universe. Conditions shortly after the Big Bang were far more energetic than anything achievable today. In such environments, compactified dimensions may have been accessible. As the universe expanded and cooled, the extra dimensions may have curled tightly while the familiar ones extended. This dynamic evolution would effectively trap matter and radiation in three-dimensional space while freezing higher dimensional structure beyond reach. Though the present-day universe carries only faint echoes of that early state, the existence of compactified dimensions remains consistent with cosmological models. The smallness of hidden dimensions has sometimes been compared to the diameter of a tiny loop at the edge of a thread. Yet the analogy does not fully capture the complexity of the geometry involved. Calabi-Yau manifolds are not simple circles, but intricate spaces with many topological features. Their sizes may be uniform or vary from point to point. They may vibrate, twist, or deform in ways that subtly influence the properties of particles and fields. These variations remain hidden because they occur on scales far smaller than any observational method can probe. Another perspective comes from considering how energy interacts with geometry. Motion into an extra dimension requires energy related to the size of that dimension. If the dimension is extremely small, the required energy becomes enormous. In effect, the dimensional structure becomes rigid at macroscopic scales. Only the most energetic processes, perhaps those in the early universe or within extreme astrophysical environments, could push matter into higher dimensional motion. For ordinary conditions, the extra dimensions remain inaccessible. The confinement of matter to three-dimensional branes provides another layer of invisibility. Branes act as surfaces within higher dimensional space, restricting the motion of particles and forces. Strings attached to branes cannot detach or move into the bulk unless given extraordinary energy. This confinement creates the illusion of a three-dimensional universe, even if the surrounding space contains many more directions. The brane becomes both a habitat and a boundary, shaping the physics experienced within it. These ideas may suggest that higher dimensions lie entirely beyond reach. Yet, in theoretical models, branes can ripple, oscillate, or drift through the bulk. Such motion could influence the evolution of the universe. In some scenarios, interactions between branes create energy bursts resembling cosmic inflation. While such models remain speculative, they demonstrate that higher dimensions can influence physical processes indirectly, shaping the structure and history of the cosmos without ever becoming visible. The hidden nature of extra dimensions, then, is not an obstacle to their existence, but a natural consequence of scale, confinement, and sensory limitations. The familiar world is not the whole of space-time, but a subset shaped by biological and physical constraints. Higher dimensions may be present everywhere, silently influencing the characteristics of matter while remaining beyond all direct perception. Not seeing is a property of biology, not a property of the universe. If higher dimensions permeate reality, what traces of their presence shape the world without ever revealing themselves? If higher dimensions exist, they do not remain isolated from the observable universe. Their presence would echo through certain physical processes, not as direct signals, but as subtle distortions, patterns, or imbalances that refuse to fit neatly within a purely three-dimensional framework. These traces form a quiet boundary between the visible and the hidden, where the mathematics of high-dimensional space meets the measurable structure of the cosmos. One of the clearest of these echoes lies in the peculiar weakness of gravity. Among the known interactions, gravity is astonishingly faint. Even the smallest gesture can overcome the gravitational pull of an entire planet. This disparity has puzzled physicists for decades. If all forces originate from the same physical reality, why does gravity behave so differently? One answer proposes that gravity is not intrinsically weak, but appears so, because it is diluted across dimensions inaccessible to other forces. In this framework, the gravitational field extends into the higher dimensional bulk, spreading through directions unfamiliar to ordinary matter. Only a small fraction of its influence remains confined to the three-dimensional brane where matter and radiation reside. What seems like weakness is instead a distribution effect. The field is simply not concentrated within the visible space. Experiments searching for deviations in gravitational strength at small distances aim to detect evidence of this leakage. While no definitive signal has been found, the idea remains consistent with theoretical models. Another potential trace of higher dimensions emerges in the study of cosmic origins. The early universe was a furnace of extraordinary temperature and density, conditions under which compactified dimensions may not yet have been tightly curled. During these earliest instants, the fabric of space-time might have vibrated freely in all available directions. As the cosmos expanded and cooled, the familiar dimensions grew large while the others contracted, becoming hidden. If this interpretation is correct, the imprint of those early multidimensional vibrations may linger in the distribution of matter, the structure of cosmic background radiation, or the behavior of fundamental particles. Some cosmological models explore the idea that the Big Bang itself may have been an event triggered by interactions between brains. In this picture, brains drift through the bulk like vast sheets of energy and geometry. If two brains collided, the impact could release immense energy, producing a hot, expanding region resembling the initial state of a universe. This scenario does not replace the standard cosmological model, but offers an alternate interpretation of its beginning, rooted in the geometry of higher dimensional space. The behavior of dark matter presents another subtle hint. Dark matter exerts gravitational influence, yet interacts little, if at all, with ordinary particles. If higher dimensional objects, such as particles living on adjacent branes or fluctuations in the bulk, hover near the three-dimensional universe, they could produce gravitational signatures without emitting detectable radiation. These influences would resemble dark matter, creating the illusion of unseen mass shaping the movement of stars and galaxies. Although speculative, this interpretation aligns with the idea that the visible universe may be one of many layers in a broader spatial structure. Adjacent branes may pass close enough for their gravitational fields to interact, yet remain separated by distances imperceptible to any instrument that operates strictly within the three familiar dimensions. In such a setting, the universe would be embedded in a larger landscape where invisible structures leave faint but measurable imprints. Even within the familiar world, there are phenomena that quietly suggest deeper structure. The propagation of gravitational waves, the ripples in space-time created by massive accelerating objects, offers a means of testing whether the waves lose energy into higher dimensions. If a portion of their amplitude dissipates through the bulk, their observed intensity would weaken in a way not predicted by three-dimensional physics. As detectors become more sensitive, comparisons between theoretical predictions and observations may reveal whether these waves behave as though additional directions exist for them to explore. In particle physics, high-energy collisions generate fleeting states that probe the geometry of space. If extra dimensions are present, certain processes might produce effects that appear as missing energy, particles that carry momentum into directions beyond the reach of detectors. Such signatures, though rare, represent one of the few experimental avenues through which higher dimensions might reveal themselves indirectly. These possibilities do not claim that extra dimensions have been observed, nor that they must exist. Instead, they demonstrate how naturally the concept emerges when attempting to resolve puzzles such as gravity's weakness, the nature of dark matter, and the origins of cosmic expansion. Higher dimensions offer a unified framework capable of linking seemingly unrelated mysteries. The traces they leave behind, subtle distortions in gravitational behavior, irregularities in cosmic structure, unexplained gaps in particle interactions, form a pattern that encourages further exploration. The idea of branes drifting through the bulk also invites consideration of how physical events might unfold when different layers of dimensional structure interact. In some models, the distance between branes could fluctuate over time. A momentary narrowing of that gap might strengthen gravitational influence from an adjacent brane, altering the motion of matter in slight but detectable ways. Such a phenomenon would not signify a breach between universes. It would simply reflect the geometry of higher dimensional space, evolving according to its own dynamics. Another trace of hidden dimensions may lie in the stability of physical constants. The values of fundamental quantities, such as the strength of forces or the masses of particles, depend on the geometry of compactified dimensions. If this geometry shifts even slightly, the constants may vary over cosmic timescales. Observations of distant stars and galaxies provide a means to test whether these constants have remained fixed or changed in ways consistent with the evolution of extra-dimensional structure. Across these scenarios runs a common thread. Higher dimensions do not reveal themselves through direct perception, but through the behavior of the universe at its extremes. Their influence emerges not in everyday experience, but in the earliest cosmic moments, in the propagation of space-time ripples, or in the gravitational pull of unseen structures. They shape the universe quietly, leaving signals at the boundaries of measurement. Despite the theoretical elegance of these ideas, they remain grounded in the restraint required of scientific exploration. The presence of hidden dimensions is not assumed. It is inferred only when it helps unify observations that resist explanation within a purely three-dimensional framework. Even then, such inferences remain provisional, awaiting confirmation or revision as new evidence emerges. Still, the notion that dimensions beyond visibility may be woven through the universe invites a gentle sense of wonder. It suggests that the familiar world is part of a broader structure, one in which unseen directions influence the evolution of galaxies, the behavior of particles, and the propagation of gravity. The boundaries of perception do not mark the boundaries of existence. They simply define the portion accessible to organisms built on a certain scale. Awareness of the universe always begins from inside a brain. Long before physics speaks of extra dimensions, each nervous system builds an internal map of reality, stitched together from signals that are incomplete, noisy, and limited. That map feels solid, continuous, and three-dimensional, yet it is constructed from fragments that do not resemble the world directly. Any attempt to understand higher dimensions must pass through this filter, because all ideas about space, time, and geometry arrive through the same biological interface. At the simplest level, perception already transforms dimensionality. Light from the outside world carries information about three-dimensional scenes, but it reaches the eyes as patterns on two curved surfaces, the retinas. Each retina receives a two-dimensional projection of the environment, flattened and ambiguous. Many different three-dimensional arrangements could, in principle, produce the same pattern of light. Yet the brain reconstructs a stable sense of depth, shape, and distance so reliably that the reconstruction feels identical to the world itself. The third dimension, in lived experience, is not seen directly, it is inferred. This reconstruction depends on many cues. The difference between the two eyes, changes in sharpness, motion, perspective, and memory of how objects usually behave. From this mixture, the brain generates a model in which surfaces stand out, objects occupy space, and distances separate them. But the internal representation still does not contain every aspect of the environment. It compresses and discards information, preserving only what is useful for navigation and survival. Hidden behind seamless experience lies a complex computation that turns incomplete data into a world. In this sense, perception already operates as a dimensional filter. The physical environment contains far more variables than can ever be represented in awareness. Every particle in a room has its own position and momentum. Every photon carries a direction, a wavelength, and a phase. The full state of even a tiny region of space can be described only in an extremely high-dimensional space of possibilities. Yet, conscious experience condenses this intricate structure into a small set of features: a wall, a table, a sound, a patch of light. Many dimensions are collapsed into a manageable interface. Some researchers have proposed that perception functions less like a window and more like a desktop on a computer. Icons on a screen do not reveal the voltages and circuits beneath. They simplify and hide them. In an analogous way, the brain may present a user interface of colors, shapes, and objects, concealing the underlying complexity of physical processes. The interface is not false, it is pragmatic. It presents enough structure to act, without revealing everything that exists. This perspective has implications for how claims about higher dimensions are interpreted. When subjective experiences feel larger than ordinary reality, when dreams seem more vivid than waking life, when moments of insight arrive suddenly, when déjà vu creates a sense of repetition in time, it can be tempting to assign these feelings to other dimensions. Yet they arise within a system already known to compress, distort, and reframe information in service of efficiency. Consider déjà vu. The sensation that a present moment has been lived before often appears unexpectedly without any clear cause. From the inside, it can feel as though time has folded, or as though two timelines have collided. But studies of memory and perception suggest other explanations. A similarity between the current scene and a partially forgotten memory may trigger a familiarity signal without recalling the original context, producing the impression of repetition. Minor timing mismatches between different neural pathways can also produce a feeling that the present has already been registered once. In both cases, the experience emerges from the dynamics of memory, not from a literal encounter with an alternate dimension. Dreams and altered states provide another example. During sleep, the brain freely recombines memories, emotions, and fragments of sensory data, creating scenes that defy ordinary logic. Distances shift, identities merge, and time jumps. A single step may carry dream consciousness from one country to another. A moment of narrative can span years. Upon waking, these experiences can feel like glimpses into other realities, because they violate the usual constraints of three-dimensional space and linear time. Yet they occur entirely within a neural system temporarily decoupled from external input, exploring its own representational space. That representational space itself is high-dimensional. Neural activity patterns do not live in physical space, but in an abstract space of firing rates and connections. When those patterns are visualized mathematically, they often occupy structures that cannot be drawn in 3 dimensions. Cognition moves along trajectories in this internal space, passing through regions associated with perception, memory, language, and emotion. The brain navigates high-dimensional configurations, but awareness experiences the result as a coherent stream unfolding in a familiar world. In this way, the brain already hides dimensions from its own experience. It operates in an extremely high-dimensional state space, but presents only a low-dimensional summary to consciousness. Complex patterns of neural activity are compressed into simple feelings: recognition, confusion, curiosity, calm. The underlying structure remains inaccessible, even though it shapes behavior and thought. Because this compression is invisible from the inside, it is easy to mistake its limits for the limits of reality. The edge of what can be represented feels like the edge of what exists. Speculations linking consciousness directly to higher spatial dimensions often arise from this mismatch between inner richness and outer description. Thoughts and feelings can change abruptly without any obvious external cause. Memories can surface from decades past, seemingly unbidden. Insights can connect distant ideas in a single leap. These phenomena can feel as though they originate from beyond ordinary space and time, yet they may simply reflect the brain's ability to reorganize its own internal structures, drawing on stored information and existing connections. This does not imply that consciousness is trivial or that subjective experience is an illusion. It acknowledges instead that the mechanisms producing experience are themselves layered and complex. Many neurocognitive processes never become conscious. They act as hidden dimensions of mental life. Language comprehension, visual recognition, motor control, and emotional regulation all involve sophisticated computations that rarely enter awareness. Only their outcomes do. The mind, in this sense, already lives among unseen layers, though they are neural rather than spatial. Misinterpretations emerge when such internal layers are conflated with external dimensions. The feeling that a decision was influenced by something deeper does not require a hyperspace to explain it. It requires only an appreciation that the brain integrates more information than awareness can display. The sense that an event carries special significance can arise from pattern detection systems tuned to notice coincidences, even when they occur by chance. When these processes operate just beyond the boundary of conscious inspection, they can feel like messages from elsewhere. At the same time, studies of perception reinforce a key lesson from higher dimensional physics. What is experienced is always a projection. Just as a three-dimensional object casts many possible two-dimensional shadows depending on the angle of light, the high-dimensional structure of the world can cast many experiential shadows depending on how sensory systems and brains sample it. Change the sampling method, different senses, different neural architecture, and the experienced reality would likely change as well. Imagining a higher dimensional being through this lens becomes more concrete. Such a being would not simply see more directions in space. It would possess a different perceptual interface, tuned to structures that three-dimensional organisms cannot access. Its world of experience would reflect the dimensionality of its environment and the design of its sensory systems. Just as humans do not directly perceive electromagnetic fields outside the visible spectrum, a four-dimensional organism might not directly perceive certain properties of its own higher dimensional context. It too would construct a partial model. This symmetry offers a sobering insight. Even if additional spatial dimensions exist, an organism living within them would be no more omniscient than a human being is within three. Perception would still be selective. Representations would still be compressed. Awareness would still receive only a filtered view of the total structure. Dimensional richness does not automatically confer complete understanding. It simply expands the range of what could, in principle, be represented. The intersection between consciousness and higher dimensions, then, is not evidence but analogy. The brain's tendency to hide complexity behind a simple interface mirrors the way extra dimensions may hide behind the apparent simplicity of three-dimensional space. Both systems suggest that what is seen is not all that exists, and that interfaces, whether neural or geometric, shape the form of experience. From this perspective, experience is often attributed to higher dimensions. Déjà vu, vivid dreams, sudden insights, altered time perception become valuable not because they prove the existence of hidden spatial directions, but because they reveal how much of mental life unfolds beyond the narrow spotlight of awareness. They show that a large part of reality, even within a single nervous system, is structured in ways that cannot be directly inspected. The unknown begins inside, long before it is projected onto the cosmos. This leads gently back to the central theme of dimensional thinking. Physics suggests that the universe may contain more spatial directions than can be accessed directly. Neuroscience shows that the mind operates in more functional dimensions than awareness can grasp. In both cases, a lower dimensional projection stands in for a higher dimensional structure. The risk lies in mistaking the projection for the whole. Attempts to imagine higher spatial dimensions often begin with analogies, yet analogies eventually reach their limit. Beyond that point, the question must be treated not as metaphor, but as geometry. What changes in experience arise when the number of accessible spatial directions increases? A higher dimension is not a new world or an alternate reality. It is an expansion of the possible directions in which position, motion, structure, and separation can be defined. And from this expansion, entirely new forms of interaction follow. In three-dimensional space, every object is bounded. Surfaces enclose, volumes define interior and exterior. A sealed container prevents motion from crossing its walls. An object blocks the view behind it. Distance restricts access. These constraints derive from the limited set of directions available. Add one more, and the constraints loosen. Add several more, and they dissolve into new forms. Understanding what it means to step into a higher dimension begins with recognizing that dimensionality shapes the very grammar of physical existence. Consider the notion of containment. A three-dimensional body surrounds a region of space. Every path from inside to outside intersects its boundary. In a world with four accessible spatial dimensions, that logic changes. An additional direction provides an escape route that bypasses the enclosing surface entirely. A sealed room loses its rigidity. A closed loop becomes permeable. Any form of confinement defined by three-dimensional barriers becomes incomplete once a new axis exists. Objects that appear locked or sealed in the familiar world become as accessible as regions on a map with overlooked paths. Separation undergoes a similar transformation. In three dimensions, two objects can be positioned with clear distance between them. That distance prevents direct interaction unless a physical connection bridges it. In a higher dimensional environment, separation can be bypassed simply by moving through an axis unavailable in three-dimensional space. What appears distant when constrained to a limited set of directions becomes adjacent when placed within a larger coordinate system. Spatial organization is reinterpreted, and with it, the relationships between points, surfaces, and structures. Even the idea of physical form must be reconsidered. A being with access to an additional dimension would not simply appear elongated or stretched. It would possess components distributed along a direction unseen by three-dimensional eyes. A higher dimensional structure projecting into three-dimensional space would appear differently depending on the angle of intersection. A single entity could manifest as several disconnected shapes, or as a shape that changes abruptly as it slides through the familiar world. From the standpoint of higher dimensional geometry, these discontinuities are no more mysterious than the changing silhouette of a rotating object. Motion also gains new properties. With an extra axis available, paths multiply. A trajectory that seems impossible, moving from one enclosed region to another without crossing the separating wall, becomes a straightforward step. Obstructions lose their solidity. The logic of navigation changes from navigating around obstacles to navigating beyond them. The environment becomes more permeable not because matter becomes intangible, but because geometry expands. Time, too, takes on a new form when approached from a higher dimensional viewpoint. In three-dimensional experience, time defines a sequence of events that unfolds irreversibly. Each moment replaces the last, forming a single thread that cannot be rewound or skipped. But from the perspective of a being with access to an additional spatial dimension, the world line of any object becomes a structure that can be observed rather than merely lived. What appears within three-dimensional experience as a flow becomes in higher dimensional view a trajectory laid out in full, one that can be examined from different angles, just as a curve in a plane can be viewed from above or from the side. This does not imply that events can be changed at will. Even in higher dimensional theories, causality constrains what can be altered. Rather, it means that the entire timeline becomes available as a geometric object. A lifetime is no longer known only from the interior, it becomes visible as a whole. The significance of each decision, the branching of possibilities, and the structure of cause and effect all acquire spatial qualities, not because time ceases to exist, but because its representation changes. Identity must also be reconsidered under higher dimensional geometry. In three dimensions, a person's form, history, and boundaries appear fixed. But when the number of accessible directions increases, the correspondence between internal structure and outward appearance becomes more complex. If a being possesses components extending into a higher dimension, then the three-dimensional profile visible in ordinary space reveals only part of its structure. Different slices of that being could manifest differently, depending on how its higher dimensional form interacts with familiar space. The notion of a single constant appearance becomes incomplete. This does not imply multiplicity of selves or supernatural variation. It simply follows the logic of projection. A multidimensional object can exhibit many three-dimensional cross-sections, each representing a partial view. Stability would still exist, but it would be defined across dimensions rather than within them alone. The continuity of a being's existence would be preserved, just expressed through a richer geometry. Physical laws would reflect this enrichment. Field lines, forces, and trajectories would extend into the new dimension. Systems would exhibit behaviors impossible in lower dimensional environments. For instance, structures that cannot be knotted in three-dimensional space might become knot-like configurations when allowed to twist through additional axes. Conversely, knots that appear stable in three dimensions might unravel instantly when moved through a higher dimensional direction. Stability itself becomes relative to the number of accessible dimensions. Electromagnetic, weak, and strong forces may remain confined to a lower dimensional brain, but gravity, already predisposed to propagate through the bulk, would take on new spatial characteristics. Objects moving through the additional dimension could influence gravitational fields in ways that appear subtle or unexplained from a strictly three-dimensional perspective. Mass distributions might exert effects inconsistent with visible structure, not because of hidden matter, but because of hidden geometry. The most striking consequence of stepping into a higher spatial dimension is the transformation of perspective. Perspective is not merely viewpoint, it is the structure of relationships among objects, distances, and directions. When an additional axis becomes available, the network of relationships expands. What appeared complex from within a three-dimensional viewpoint may simplify when seen from a broader frame, much as a complicated path on a map becomes straightforward when viewed from above. Problems that seem intractable under lower dimensional constraints may lose their complexity when treated as projections of higher dimensional structure. Yet, complexity also grows. New paths, new surfaces, and new interactions introduce patterns that cannot exist in fewer dimensions. The environment becomes richer, not only in navigational possibilities, but in structural diversity. Patterns of motion acquire intricacy. equilibrium states multiply. New forms of stability and instability arise. The expansion of dimensionality introduces both simplicity and complexity, depending on the scale and the perspective from which a phenomenon is examined. Importantly, stepping into a higher dimension does not imply gaining omniscience. Just as a human observer in 3 dimensions perceives only a portion of the full physical state of the world, a being in 4 dimensions would be limited by its own sensory architecture. It would construct its own simplified model of reality, shaped by its needs, constraints, and evolutionary pressures. Each level of dimensional access brings both freedom and limitation, not an escape from the boundaries of perception, but a shift in where those boundaries lie. The act of stepping itself requires clarification. In the context of physics, stepping into a higher dimension is not a literal movement, but a hypothetical extension of the coordinate system governing position. For an organism confined to a 3-dimensional brain, motion into an additional dimension would require escaping the forces that bind matter and radiation to the brain. Such an event remains outside current understanding of physical processes. Thus, the idea is treated as a thought experiment, a way to explore how geometry shapes experience. From this perspective, to imagine stepping into a higher dimension is to imagine perceiving more directions than are currently accessible. It is to imagine observing structures not as fragmented slices, but as cohesive wholes. It is to imagine navigating around barriers rather than through them, and interpreting relationships not as sequences, but as patterns laid out in full. The exercise reveals not how a future discovery might unfold, but how deeply dimensionality influences the very notion of existence. Crossing into a higher dimension would not change the universe. It would change which parts of it become visible. The structures already exist, whether or not they can be sensed. Dimensionality determines the window through which those structures are encountered. When the window widens, experience transforms, not because reality shifts, but because more of it becomes available. As the exploration reaches its quiet end, the landscape of higher dimensions no longer appears as a distant abstraction, but as a natural extension of the universe's internal logic. Each chapter unfolded not as an argument for what must be true, but as an invitation to observe how consistently the idea of additional dimensions emerges whenever physics attempts to unify what appears separate, to explain what appears irregular, or to reveal structure beneath what appears familiar. The world has not changed through this journey. Only the frame through which it is considered has widened. Dimensionality has always shaped experience long before it became a subject of mathematics. The ability to move, to see, to build, to understand, all depend on the number of directions accessible. These directions define every boundary and every possibility. Yet the mind, evolved to navigate daily life, seldom questions why the world has exactly the form it does. When the question is finally raised, the simplicity of the answer gives way to a remarkable depth. The universe might contain more structure than perception can reveal, and the familiar world may be only a projection of a larger, unseen geometry. Physics reached this idea not through speculation, but through necessity. Whenever the fundamental forces resisted unification, additional dimensions offered consistency. Whenever particles behaved in ways that demanded deeper explanation, higher dimensional models restored coherence. Whenever geometry appeared insufficient to describe the motion of energy and matter, extending the coordinate system made the equations whole. In these patterns lies the quiet suggestion that dimensionality is not an arbitrary feature of reality, but a foundational principle. Yet, even as theoretical frameworks widen, the visible universe remains the same. Stars continue their slow evolution. Galaxies drift through intergalactic dark. Matter clumps, collapses, forms, and disperses according to laws that remain consistent across billions of years. Whether the deeper fabric contains 6, 7, or 11 spatial directions does not alter the stability of the night sky. What changes is the interpretation, a shift from viewing the cosmos as a self-contained 3-dimensional construction to seeing it as one layer of a more intricate whole. The idea of higher dimensions often evokes expectations of dramatic revelation, as though stepping into a new direction would unlock a realm completely separate from the one already known. But dimensional expansion is quieter than that. It alters relationships, not existence. Boundaries become permeable, distances become relative, Sequences become structures. Stepping into a higher dimension, if such a step were physically meaningful, would not replace the present universe but place it within a larger context. What felt complete would become part of a wider arrangement. There is a subtle comfort in this perspective. It suggests that the universe is neither closed nor limited. Instead, it accommodates layers that remain unseen only because no biological or technological instrument has yet found a way to access them. These layers are not hidden in the sense of being distant. They are hidden in the sense of belonging to directions unused by matter and radiation confined to familiar space. The absence of direct perception does not diminish their plausibility. It reflects the boundaries of consciousness shaped by the dimensions that have guided life since its beginning. The question that guided this entire journey, what would happen if a being could step into a higher spatial dimension, remains open, but it is no longer vague. It now rests on a scaffold of geometric reasoning, physical principles, and the natural behavior of systems in expanded spaces. The answer is not a catalog of miracles, but an understanding of how experience changes when constraints shift. Interiors become visible. Paths once impossible become trivial. Structures once fixed become flexible. Time itself acquires new representation. These transformations follow not from fantasy, but from consistent mathematical extension. At the same time, the limitations of such an exploration must be acknowledged. Theoretical models point toward the possibility of higher dimensions, but they also impose boundaries on what can be concluded. No experiment has yet confirmed the existence of additional spatial directions, and no observation demands them as the only explanation. Their value lies in how effectively they integrate what is known with what remains uncertain. Whether they ultimately reflect physical reality or serve as temporary scaffolding for deeper theories, they shape understanding in a meaningful way. Reflecting on this entire arc, one finds that the most striking insight is not about dimensions themselves, but about perception. The senses reveal only a portion of reality, and the mind constructs coherence from incomplete information. Higher dimensions challenge the assumption that what is seen constitutes the whole. They encourage a posture of humility, the recognition that the universe may be structured in ways that exceed both language and intuition. Yet rather than diminishing the familiar world, this recognition expands its significance. Each observable pattern becomes a doorway into something deeper. There is a particular stillness in the idea that reality might be broader than direct experience suggests. It invites neither fear nor urgency, but a quiet appreciation for complexity. If additional dimensions exist, they accompany every moment, woven into the fabric of each interaction. They remain unseen not because they are silent, but because their influence expresses itself through subtleties, the weakness of gravity, the shape of cosmic evolution, the stability of matter, the elegance of mathematical symmetries. These traces compose a gentle presence, offering hints without revealing form. As the narrative closes, the concept of dimensionality returns to its simplest expression. A dimension is a direction, an axis along which change, position, and relationship can be defined. Life in 3 dimensions unfolds along the directions available. If more dimensions exist, then reality holds more directions than can be sensed. And if reality holds more directions than can be sensed, then every structure, every motion, every existence is richer than it appears. Nothing about the familiar world is reduced by this idea. It is only placed within a larger space. A quiet sense of wonder emerges from this perspective. Not the wonder of spectacle, but the quieter wonder of possibility. It is the recognition that understanding is always provisional, that the universe offers more than can be measured, and that the boundaries of knowledge are not the boundaries of reality. Higher dimensions may never appear in the way the imagination first conceives them, yet their conceptual presence enlarges the space in which thought operates. They offer a reminder that the cosmos accepts complexity without hesitation. The journey ends here, but not with finality. It ends with openness. The question that began the exploration remains alive. What would happen if a being could step into a higher spatial dimension? The answer, shaped through physics and geometry, is neither definite nor closed. It remains suspended at the edge of what is knowable, and perhaps that suspended state is the most fitting conclusion. For in the space between certainty and possibility lies the essence of curiosity. If reality contains more than what is seen, understood, or named, then every moment may be accompanied by layers that slip quietly beyond perception. They do not alter the course of daily life, yet they lend it depth. They form the unseen scaffolding behind every motion, every structure, every star. And in their presence, even unobserved, the universe becomes not smaller, but larger, not simpler, but more intricate, not closed, but open. This journey pauses with a simple understanding. The space we know is not necessarily the whole of what exists. Beyond what can be seen or measured directly, reality may include directions and structures that remain hidden, not because they are unreachable, but because they lie outside ordinary perception. Whether these deeper layers ever become visible does not change their role in shaping the universe we already inhabit. For now, that possibility is enough. Nothing more needs to be resolved tonight. The cosmos continues on its own, and the mind is free to rest alongside it. Good night.